Hello, hello. Yeah, so you can hear me now. Yes, thank you very much for presenting here. I'm actually honored to be here to talk something about our research. So this actually, I realized that this conference is very theoretical, but my talk is about some experimental astrophysics. So hopefully you can get some information from this talk about what we know about this high energy part of the universe. I'm from the Purple Mountain Observatory of CAS. So this is the outline. So I will try to describe briefly the background about this study. And basically, we use the facility. This is a big facility in China about the cosmic observation. In short, it's LHAASO. So it's in the Sichuan province. It's a square kilometer size array to detect the high energy particles in the universe. And this is the third part is about this diffuse gamma ray measurements we did recently with this LHAASO experiment. This is actually the title of this talk. This is a very brief overview of cosmic rays. Those are high energy relativistic particles from the outer space hitting the Earth. And it was discovered by Victor Haas in more than 1 century ago. So this discovery actually Haas won this Nobel Prize in 1936 with this discovery. So the cosmic rays including almost all these elements observed on Earth. So yeah, we will see that this red is the solar system abundance. That's for this background medium abundance. And for cosmic rays, we see that almost all these kind of particles there with different abundances from this medium. That may be due to their production or acceleration mechanism. And in the past, there is a golden age of cosmic ray study. In this cosmic rays, people discovered many new particles. Some are fundamental particles in cosmic rays. I think at that time, people just use cosmic rays as a natural collider to do this particle physics study. Like the positrons, muons, some hadrons, pions, kaons, and there are many hadrons were discovered in cosmic rays. Those discoveries actually helped us to build the standard model of particle physics. Nowadays, I think cosmic rays have broad relationship with new physics. Like we can use cosmic ray to probe the dark matter, to study the acceleration or interaction at this ultra high energies. And we also can study some extreme astronomical phenomenon, like this objects at very strong gravity, very strong energy, strong density in such conditions. So what we know about cosmic rays, so basically we have those observables. The one is this called the spectrum. This is the energy and their flux. So roughly we see that cosmic rays has a declining power law distribution of their spectrum. And for different species, we have some different, somehow different spectrum shapes. And there are also some structures on this overall spectrum. So try to understand why those particles have this kind of shape and why they have these structures like the knee structure, this ankle structure, and some other structures. This is the main topic of the cosmic ray study. The second one is their arrival direction. Also, we can call it as anisotropy. So because most of the particles are charged particles, so they will get deflected in the magnetic field. So when they arrive the Earth, most of this direction actually get disappear about their source direction. So those particles will arrive at the Earth almost isotropically, but have very tiny anisotropy. So this anisotropy amplitude is something like 10 to minus 3. So if we observe those directions very precisely, we figure out that they have this kind of anisotropy. It's a dipole, and if we remove this dipole, we have some high order anisotropies of this arrival directions. And the composition is the same. Yes. This dipole, I think, the main understanding is that they may come from this. We have a local magnetic field structure. It's those particles will somehow aligned with this local magnetic field structure. But after remove this dipole, we also have some high order anisotropy that may have more complicated physics. This composition, most are protons, and then we have like 10% alpha particles and some heavy nuclei. This composition actually is similar with the composition of the universe. Finally, we have time variations of the cosmic flux. So this time variations mainly reflect the solar activities. So it has this 11-year period of this time variation. So those are questions that we are trying to understand about cosmic rays, like where do they come from, so the origin of these particles, and how they are accelerated, especially to the extremely high energies. So the highest energy particles in cosmic rays is like 10 to 7 times higher than the LHC energy. And how they propagate and interact in the universe. So this is a propagation problem, and how to form those spectral structures, and also this anisotropy and their evolution with energy. This is also the issues. We have some answers of these questions, but we do not understand them fully. So we are still trying to study those issues. And one important thing is that do those particles can reflect some celestial objects as a multi-messenger probe. So we know that currently we have this electromagnetic wave observation, the gravitational wave observation, also the neutrino observation. Can we observe those like cosmic ray particles from those objects? So we can use this multi-messenger approach to try to understand the physics of those objects. And finally, and this is a very important question, is that do they connect with new physics, like this dark matter? What is the nature of dark matter? For this, this talk actually mainly focus on this galactic component of cosmic rays. So this is a general picture of those particles in the Milky Way. So they are like accelerated from some sources like the supernova remnants, and then they will propagate mainly diffusively in the Milky Way. And during this process, they will interact with the medium to produce secondary particles and also secondary radiation. And part of them may come from the annihilation or decay of dark matter. So this is the, we use the precise observation of cosmic rays to try to detect those dark matter particles indirectly. So this is called the indirect detection of dark matter. So for the detection aspect, we basically have two methods to detect particles. The one is called direct detection. So we launch satellites or some balloon experiments to try to detect those particles just on top of the atmosphere. So in this way, we can measure those particles precisely what their charge is, what the energy is, and their direction. So this is called a direct direction. But the issue is that we can only launch some small detector in the space, and the cost is also high. So for this technique, we basically detect the low energy part of the spectrum, because we have many particles in the low energy end. If we want to detect the high energy part of the spectrum, this method cannot be used anymore. However, we have a complementary method called indirect detection. So for high energy particles, when they interact in the atmosphere, they will produce secondary particles. Secondary particles will interact again to produce tertiary particles, and those interactions will it can happen many times, and then we can have quite a number of secondary particles by this interaction. So we can build a very big array to collect all these secondary particles and then try to reconstruct what their original particle is. So this is we call the indirect detection methods. In this way, so the detector size can be large. Currently, the biggest one, I think, is in this Argentina. The size of this detector is 3,000 kilometer square. So that's a very big size detector. So this picture is from this Tibet, this Yanbajin Observatory. So its size is something like 40,000 meters square. So this indirect detection, it can detect particles to very high energies, but the issue is that for this way, the particle identification is somehow difficult. For example, if we have one particle, proton for proton or helium, it can hardly to distinguish them. So these two methods are complementary with each other. Currently, we have a number of experiments in space, like we have those typical experiments. Also on the ground, we also have quite a number of experiments. So now I come to our experiment called LHAASO. The full name is Large High Altitude Air Shower Observatory. So it's located in the Sichuan province. The altitude is 4,000 meters above the sea level. And this is a bird view of the detector. So it covers 1.3 kilometer square area, and it has some hybrid detector arrays. It has this KM2A, a square kilometer array, and in the central part, we have this water Cherenkov detector array, and around this central part, we also have some telescopes, a wide field view Cherenkov telescope array. So it started its construction, it ended the construction in July 2021 and started the full operation. So this basically shows the principle of this detector to, sorry, so this actually is an animation, but if it's a PDF version, it cannot work. Anyway, for a particle enter the atmosphere, it will produce secondary particles, and we use different detectors to record the different components in this air shower. So for example, we have this particle detector to detect electrons, positrons, or muons in the shower, and we use this telescope to record the Cherenkov light produced by those particles. This is the KM2A instrument, some detailed picture about the detector. So we have electromagnetic detectors over 5,000 units. This is to reconstruct the energy and the direction. So basically, we use this the total amount of particles we recorded that's roughly proportional to the energy of the primary particle. And we use this arrival direction of those particles to reconstruct the direction of our particle. If, for example, if one particle comes from this direction, so the detector in this part will get fired earlier than the detector in this part. So we can use this time difference to reconstruct the direction of our shower. And we use the muon detectors. The muon detectors, this is basically used to distinguish particles, basically distinguish photons or electrons from the nuclei. Because for nuclei, they will produce this air shower with many, many muons. But for this electromagnetic particles, for photons and electrons, the muon content is much less than the nuclei. So this plot just shows a simulation result, shows that this is number of muon and the number of electrons. So for gamma rays, it's basically in this part, and for protons in this part. So we can use this detection of muon to distinguish those different particles. And this is the water Cherenkov detector array. This area is like this. And this is the inside of this detector array. So we have many, many PMTs, the photon PMT, photon multiple amplifier detector. And this is the water. So when the secondary particles propagate in the water, they will produce a Cherenkov light. And this Cherenkov light will be recorded by these PMTs. And yeah, here shows this telescopes. This is called a wide field Cherenkov telescope array. So this is also to detect the Cherenkov light, but those Cherenkov light are produced by this Cherenkov radiation in the air, in the atmosphere. And we use this 18 telescopes to point to different directions. And this is the size of each telescope, and covers a square sky with this area. And they use this Cherenkov observation, this air Cherenkov observation, we can distinguish different particles basically by their mass. For example, we can distinguish protons from iron, from heavy nuclei, the different mass groups. And the objectives of LHAASO basically have these three objectives: to probe the origin of cosmic rays via this precise measurements of their spectrum and anisotropies, and to survey this very high energy, actually we can call it ultra high energy gamma ray sky with very high sensitivity, and then to probe new physics, possible new physics. So here I show some results obtained with this LHAASO experiment. So this actually basically the first science paper about the use the LHAASO partial array. So actually it's yeah. 10 to oh, it's a PUA, right? Yeah, 10 to 15. Okay. Yes, so we use a part of the detector array, and we discovered a number of PUA sources. So now they have a name. We call it a pivotron. Basically, it's it's similar with this Collider, the name used in the Collider study. So that means those sources can accelerate particles to PUA energies, and it can successfully open the PUA window. So this is, I think, for the first time we observed the PUA gamma rays from the universe. And this is an observation of this called Crab nebula. It's a standard candle in the universe. So the Crab nebula is bright in many wavelengths, from radio to infrared to optical, X-ray to gamma ray to this very high energy gamma range. So it's very bright. So usually we use this source to calibrate our detector. Whenever we have a new detector launched, we first observe this Crab nebula and try to see what the performance of the detector is, whether it's a good detector. So we use this, the LHAASO experiment to observe the Crab nebula, and we extend the spectral measurements again to PeV energies. So previously the measurements is basically extended to like hundreds of TeV, hundreds of 10 to 14 electron volts. So we extend this energy to like 1 order of magnitude to the PeV energy range. And revealing that the Crab nebula actually is a so-called pulsar wind nebula. So that means that the pulsar wind nebula is electron accelerator, it's a PeV electron accelerator. Very interestingly, we show that at this highest energy part, the spectrum shows some kind of a change from this this is a standard model prediction. So means that there are possible some new features at the highest energy end. So that may reveal some new properties of this source. For this Crab nebula, basically, I think people believe that those accelerated particles are electrons, I think. And yes, you can see this curves, actually, this is from a standard electron source model. So it can explain this radiation in actually a very bright energy range. So yeah, this part, I just cut this part. From this radio to this very high energy gamma rays, over 20 orders of magnitude energy coverage. Use this simple electron model can explain this wideband spectrum. But however, for this very highest energy part, so this somehow is a little bit difficult to be explained with this electron source. So people propose that there could be a component or proton component at this very high energy part, but this is still need to further studies. And we published in this year the first source catalog. So we observed nearly 100 sources. And in this high energy part, we observed quite a number of sources. So this catalog actually offers us quite good sample to study the very high energy particle, high energy particle accelerator. So this is also one important study. We use the experiment to discover, we call it a super pivotron. So it can accelerate particles to like 010 PeV energies in this so-called thickness region. So this region represents a new class of sources to accelerate particles, basically from this massive star clusters. So there are many young massive stars in this region, and the stars will eject some fast stellar wind, and those wind will hit on this medium, will produce shocks. Those shocks can accelerate cosmic ray particles to very high energies. So from the spectrum, again, the spectrum extend to multi-PeV energies, and their apparent particles will have an energy exceed 10 PeV. We observed extended pulsar halo It's called the extended emission around a pulsar. And we can use this radial profile of the emission to study the particle propagation around those sources. And the interesting thing shows that the particles will propagate in those in the vicinity of a pulsar with a much slower speed compared to the average value in the Milky Way. So that means this pulsar environment actually can confine cosmic ray particles around those sources. And LHAASO is very lucky to discover this highest energy from this brightest gamma ray burst. So this is called the this bold gamma ray burst, the bright all of the time. This gamma ray burst, and the LHAASO actually discovered the emission up to 10 TeV energies. And this actually has a very interesting constraint or implication on possible new physics, because we know that for those particles, for those high energy photons in the faraway objects, when they propagate to the Earth, it will interact with the background radiation like CMB and this infrared optical background. It will produce electron-positron pairs, and this will induce to absorption of those sources. So that means that if, so here you can see that, so this is the original spectrum. And after this absorption, it will go like this way. It will become very steep spectrum. So if we observe this photons with very high energies, so we can constrain how much it was absorbed during their propagation. And this can actually give us constraints on some new physics, like whether there are axion-like particles when they propagate, is there some conversion of this photons, and then the back conversion from axions to photons. So we can use this to constrain this interaction. And also we perhaps can constrain this Lorentz invariance violation issue. So in this case, it will also change the interaction of this process, and it will change the threshold of this reaction. And then we will use this observation to have this meaningful constraint on this possible new physics phenomena. We measured the cosmic ray spectrum and their mass, average mass. This is the spectrum. We show this so-called knee of the spectrum. It's very much like the knee of a person. And also this is the average mass, the logarithm of average mass shows this spectral shape. Very interestingly, we show that there have this spectrum and this mass evolution with energy has some correlation. Like when this spectrum has a break here, and the average mass also have a break here. So this kind of correlation shows some interesting implication on this cosmic ray composition, cosmic ray origin. And also we use this LHAASO as a probe to study dark matter. We obtained the best limits for heavy dark matter with PeV mass. This is our the results. So this parameter space below this curve is excluded region. So this last observation actually exclude some new portion of the parameter space, which cannot be excluded, cannot be probed by previous experiments. The other study is, again, we use this highest energy photons. We can constrain one class of Lorentz invariance violation scenario. So in this case, if there is a violation of this Lorentz invariance, it will induce some new phenomenon like this vacuum decay of photon. This photon will decay into electron-proton, electron-positron pair, or the split of the photons. So that means if we observe a very high energy gamma ray photons, so this process is actually constrained. So we use this LHAASO observation to derive the most stringent constraints on those parameters. So we basically we exclude the first order Lorentz invariance violation scenario because we constrain that this energy scale is actually much higher than the energy scale. So this scenario can readily be excluded. And for this second order LIV scale, we constrain it to 10 to minus 3 times of the Planck scale. So this is also very good progress. So then come to this second part about the diffuse gamma ray measurements with the LHAASO experiment. So for this galactic diffuse gamma rays, they are produced, this is a standard model to produce diffuse gamma rays. So when this cosmic rays are propagating in the Milky Way, in the galaxy, they will interact with this gas, interact with the medium, and those interaction will produce, mainly produce pions. This pion will decay to give this diffuse gamma ray emission. So we can use this diffuse gamma ray emission to probe the cosmic ray propagation. May have this three components of the diffuse emission. One is from this pion decay. This we call it a hadronic channel. This cosmic ray interact with the medium to produce pions. Those pions will decay to photons. And we also have the leptonic channels. For the electrons will have bremsstrahlung in the interstellar medium. And they will have inverse Compton scattering with the radiation field. So those three components add together to give this all diffuse emission. And they have different properties. For example, so this component will have strong correlation with the gas distribution, and this component also correlated with the gas distribution. But for this component, this spatial distribution is quite different from this two, because it's correlated with the radiation field distribution rather than this gas distribution. So they will have different spatial distribution. The past observations from the space, we have like this very old observation for this OSO3 experiment. I think this half a century ago. And we have a COSB mission, the Egret mission, and currently we have the Fermi mission, have very good measurement of the all sky emission. After removing those point-like sources, we can see this very bright galactic plane. Diffuse emission. This basically shows that this emission mainly comes from this component from the hadronic interaction. For this higher energies, by ground-based experiments, we also have some measurements by Milagro, by HAAS, and Argo, the Hawk. Also, there's a Tibet AS gamma experiment. Nevertheless, we see that we have those measurements, but we actually found that those measurements in the energy coverage or sky coverage are limited. Also, this precision is also limited. So here shows a summary of this wideband diffuse emission. So we see that in this high energy part, the low energy part is covered by space experiments. But for high energy part, by this ground experiments, we see these results are actually limited in both the precision and this energy coverage. particularly for this is so-called outer galactic plane region. This is for inner galactic plane that has strong emission. We have some observations there. However, for this outer galactic plane, we almost have low observation there. It's because the emission is still weak. So this is an opportunity that we can use LHAASO observation to do better job in this kind of measurements. So this is the sky coverage of LHAASO. We are in the north hemisphere, so we actually can cover only part of the sky. So basically, this blue is our field of view. For this south hemisphere, we cannot reach this part. So for this galactic plane, we basically can cover this part of this galactic plane. And to measure the diffuse emission, we need to subtract those bright sources. So we observe the very large number of bright sources. So we remove those sources from this analysis. So we based on this our first catalog, and to remove a region around those sources. So eventually we get this this is called a region of interest. So this blank region is the source region. We removed it from the analysis, and this colored region is our remained sky region. So we see that we do not have very bright sources in this region. So the highest significance of those, we have some hot spots, but the highest significance is below 5 sigma. So for this total region, we observed nearly 30 sigma significance emission from this area. And for this outer galactic plane area, we also observed the emission nearly 13 sigma significance. And we measured the spectrum. So this spectrum in these two regions. The spectrum can be described by power law form with an index of -3. And for the outer space, I want to emphasize that this is actually the first detection in this very high energy band from this outer galactic plane. We also studied the longitude and the latitude distribution of the emission. So in two different energy bands, this is a relatively low energy band and this is high energy band. So this left two shows the longitude distribution. And compared with this black line is from the gas distribution. So we believe that this highest diffuse emission will come from the cosmic ray interaction with this gas. However, the measurement shows that this correlation are not very good. So that means that this prediction, this model prediction of this gas interaction is not enough to explain the data. For this latitude distribution, this data is roughly consistent with the gas distribution. But for longitude distribution, we do see quite some deviations. And also we extract this power spectrum, angular power spectrum of the distribution, again compared with the gas. So this shows this purple line shows the gas distribution, the predicted angular power spectrum, and this black shows our data. We observed that at this low L, so it means relatively large space scale, we observed that this data is higher, the angular power of the data is higher than the gas distribution. So that means that we have some clumpy structures at those scales. And those clumpy structures may correspond to this fluctuation, this up and down of this emission. We then compared the measurement with a toy model prediction. This toy model basically shows that we have the proton, for example, the cosmic ray proton measurement, locally measured cosmic ray proton flux and the helium flux. We have some uncertainties at high energies, but at low energies, the uncertainties are somehow small. And if we assume that the cosmic ray intensity is the same throughout the galaxy, so it's the same as the local spectrum, and we just use this local cosmic rays times this line of sight gas distribution, we can predict what the flux of the diffuse gamma ray emission, what we should observe. And the prediction shows by this gray band. So the measurement is somehow higher than this prediction. So the difference is a factor of 2 to 3 in these two different parts of the galaxy. So that means that our assumption, here we have assumption that all this cosmic ray intensity is the same in the Milky Way. That may be wrong. So this may not be this. The cosmic ray may have some spatial distribution in the galaxy, like in the center of the galaxy, we have some higher intensities, or there could be some we call it unresolved source components. So for our analysis, we try to subtract this bright sources, but it's definitely you should have some component from this weak sources, some faint sources. We cannot detect them individually in the data, and the cumulative effect may contribute to this difference. You mean here? Yes, this asymmetry, I think, may come from this sky regions, because you know we mask out this sky regions, but some sources are above the plane and some are below the plane, so we perhaps can have some asymmetry. Yeah, but precisely if we do not do this kind of mask, we again have some kind of asymmetry. I think that may be due to this random distribution of the sources. It may not a strictly asymmetric distribution. So this is a toy model. However, we can have a realistic model with a cosmic propagation model in the Milky Way. So again, we try to fit the local spectrum, local observed spectrum with the output of this propagation code, with this propagation framework. We fit this proton spectrum, helium spectrum, and also we include the leptons in this model. So we fit the positron spectrum and the electron plus positron spectrum, and then we calculate all this the contribution to this diffuse gamma rays. So in this case, we actually somehow include the spatial distribution of those particles in the galaxy. So we do not again use this very simplified assumption that all these particles have the same intensity as this solar system, the local position of the solar system. In this case, we again shows that for this black one shows the total emission from the model prediction. So we see that out of this very low energy part, this prediction is consistent with the data, this measurement by Fermi satellite in this low energy part, and it's at this very high energy part, the prediction may also roughly consistent with our measurements. But for the intermediate energy range, we do observe the excess in both sky regions. We see there is some excess in this intermediate energy range. So this actually gives us some. This is of our galaxy, the Milky Way. How do we know? Basically, we observe the. Okay, I will show you the sky map. Yeah, this is our sky region actually. So we observed this component is highly correlated with the galactic plane. This is a galactic plane. We know that there is an isotropic component from this outer space. But in our analysis, those isotropic components actually have been subtracted. Yes, yes. And the other issue is that actually at this very high energy range, this isotropic component should be highly suppressed because there's gamma-gamma pair production. Yes, so we see that the X is not in all this energy band, but appear mainly in this intermediate energy band. So this is actually give us some hint that there could be some unresolved source population. So here we just do a very simple phenomenological component to add a component with power law spectrum with an exponential cutoff spectrum. So we see that if we add those component, we can recover the wideband observations quite well. And so we try to evaluate how big this unresolved source component is. And so for example, so this shows our observed flux distribution for our sources, the flux, and this is their number. So intrinsically, it should look like this way. There's a black line shown here. However, at this low flux end, we cannot detect those sources because the detection limit, we have the limit of our instrument. So we observed this flux distribution may drop here. But if we want to evaluate how big this part is, we can use this high flux part to observe this flux distribution and try to extrapolate to this low flux end. And we integrate out all this part to get this contribution. So this is a very simple idea. So we do this based on our catalog, our first catalog, and we try to extrapolate to this unresolved source part. Yes, thanks. To try to extrapolate to this. So here is this plot just shows that we observe the flux source distribution looks like this blue, and the extrapolated one just look like this red. So we can calculate how large this fraction is. The result shows that even if we add this component, we cannot fully explain the data. So here, this again, this purple band shows the expected total expected fluxes, including those unresolved component. So it's still slightly lower than the measurements, especially in this inner galaxy region. In the outer galaxy region, we, however, can, if we add this unresolved component, we can roughly explain this measurements. So that means that, again, so in this analysis, we have this very large extended sources actually was not considered in this catalog. So in this catalog, we just reported the sources with extension smaller than 2 degrees. So we perhaps have a population with large extension. And also, there may be some additional contribution from some unknown mechanism. So if there is unresolved sources, so what is the physics of the unresolved sources? This there is a population of this sources we call the pulsar halo, maybe a natural candidate of this unresolved source component. And we observed some extended halos, so this extension may be very big. So for example, for this Geminga pulsar, we observed, this is observed by Hawk experiment, this very extended source, extension like 10 degrees, something like that, sources around this pulsars. And we have many pulsars in the sky. So for this ATNF pulsar catalog, we have, I think, several thousand pulsars in the sky. So if we add all this contribution from these pulsars together, it may contribute a non-negligible fraction of the diffuse emission. So we did this theoretical modeling. We predict the gamma ray emission in this energy range based on the ATNF pulsars, but with some parameterization of their properties. And we do get that. So if we add a pulsar halo contribution shown by this green line, so it can indeed explain this data in both the spectrum and the spatial distribution. The spatial distribution is not perfectly agreement with the data, but roughly we can see that if we add this pulsar halo component, we can get some roughly consistent with this measurement of the spatial distribution. So basically this is the talk I would like to present, and a brief summary shows that the LHAASO successfully opens the PV gamma ray window and reveals a large population of pevitrons in the Milky Way. And we observed the diffuse gamma ray emission from the galactic plane with high precision. We first detected the diffuse emission in the outer galactic plane region. And the observations are different from the conventional propagation model prediction. So it means that there could be some unresolved source population, or there in some more complicated propagation scenario, people may also explain this results. We see there are some studies in literature that try to explain this LHAASO data with some alternative cosmic ray propagation model. And we also show that our pulsar halo model can properly explain this measurements. So this is an example of this unresolved source population. Okay, so thank you very much.
I don't know if you happen to know the horizon for these PEV gamma rays, how far we can see?
The horizon, I think, is almost our galaxy. It's almost our galaxy. So for example, we can simply calculate that in the CMB field, cosmic microwave background field, for a photon in the galactic center, they propagate to the Earth. The absorption probability is something like 80%. 80%.
So it's even smaller than.
Right, it's quite smaller, quite small.
Right. So then, okay, I see. So then this the constant background that you mentioned. I mean, it's not really a constant background from. I don't know why there would be a constant background, because I mean you don't see things far away, so there shouldn't be a constant background.
So you mean this constant, this isotopic background?
Yeah.
In our analysis, the isotopic background mainly from charged particles. We cannot fully identify them from gamma rays.
Okay,
So it's
I see.
becomes our background.
Nice, it's not-
And may include a small portion of electrons. For electrons and gamma rays, we cannot distinguish them. So yeah, for those charged particles, that's our background.
Thank you.
Questions? I have a small question.
Yes.
So you mentioned that from this cosmic arrays, you put some constraints on this PEV and dark matter.
Yes.
Can you again?
Yeah, so this one.
So which area is like excluded?
I think this part below this
Below,
below this curve, because we constrain the lifetime of dark matter. So that means the lifetime of dark should be long enough in order not to violate the LHAASO observation.
I see.
Yeah, because we observed some sky region and we do not find the expected excess from the dark matter decay. So we exclude those parameter space
I see.
below.
Are there any some cross tracker with other experiments for this PEV?
Yes, yeah, sure. You can see that I think here shows some curves.
I see.
Yeah, this one, I'm not sure what the experiment is, but this, I believe it's also some air shower experiments. And also we have this ice cube results. Ice cube actually gives some phase. So this case, I think, is to try to explain the ice cube observation of the neutrinos from, ice cube observed some excess neutrinos compared with the atmosphere background. And this model may try to use the dark matter decay to explain the ice cube results. And we can readily exclude those explanations, I think. Yeah, roughly, there is still some remain parameter space, but roughly we can exclude those.
Okay, thank you. If there are no questions, let's thank the speaker again.
Okay, thank you.